Bit about Jasper. Jasper's it's a fairly small company. We're actually the number 5 EDA vendor in the world, so we're not tiny. We're not a small startup. Been around for a long time. The last 4 or 5 years have really been a successful series of growth years for us. So we've been been profitable. We've been growing rapidly. Over 120 people in the company, mostly focused on technology, which is good. Our customer list is basically the who's who of system-on-a-chip design. With the semiconductor vendors, IP creators, and so forth. And that's all great. Before I get into my presentation, I want to actually use some slides that I've nicked shamelessly off ARM and Mike at TVS. This is the taxonomy of bug avoidance, bug hunting, bug absence, and bug analysis, or as Alan Partridge would have it, the aha terminology. I hope you're all paying attention, because there will be a quiz at the end. And I find this useful because Formal is such a big methodology, such a big technology. In order to deploy it successfully, you need to figure out which bits of it you're going to use or how you're going to use it. And one of the key areas is bug avoidance. And this really is about using Formal early in the design process, being adopted by designers, really. Because if a designer finds a bug, it isn't actually a bug. It's just a piece of incomplete design. It's only a bug if a verification engineer finds it. And Formal is really good at this. Bug hunting early in the design process, catching bugs before they actually need to go into a system-level environment. The other 3 letters, the H is for bug hunting. Again, one of the things that Formal is very good at. You set up a Formal environment, maybe for X-propagation checking or connectivity analysis. So at a system or a subsystem level, you can set up a Formal environment. You may not get full proofs, but you will get a lot of good bug hunting capability. Bug absence, this is classically the end-to-end property proving about a design. Very challenging at a system level or even at a subsystem level if it's a large subsystem. Can be very, very effective for key blocks in the design. And finally, if it all goes horribly wrong, bug analysis. So if you actually have a late-stage failure in the cycle, actually root causing why this chip that should not be able to do what it is doing, why is it actually doing that? And Formal is very good for root causing that and allowing you to validate fixes against that bug. So this terminology, AHA, has been adopted by ARM and I think and TVS have been deploying it as well. And I love it because it's a very good way of understanding how Formal can be adopted. So perceptions, I mean, a lot of this is background. Basically, as I said, Formal's been knocking around for ages. It's always been a bit of a curiosity. You've needed to have at least 1 PhD in mathematical methods in order to use it. It's required the adoption of strange languages or procedures, and that's really limited its use. In some cases, for some methodologies, you have to create, effectively duplicate your design as a set of properties, which is clearly a lot of overhead for what may not be adequate value. And because property languages really weren't standardized until the last few years, it's meant learning a new language as well on top of a new methodology. And I think a lot of the things with with SVA and property languages being more established in general has meant that Formal has had something to work with. We don't have to evangelize languages. It's a tool and a methodology. And a lot of the work that Jasper has done has been in making it usable and adoptable by non-specialists. And this is one slide that is possible to talk about for about 2 hours. These are the different areas in which Jasper Formal products are used. So as well as the core, Formal property verification, which is the property proving, basically, there are a whole series of different apps. Marketing decided to call them apps because apps, as we know, are cool, and they cost about 49p each. Although that's not true in the case of these apps. So what I'll tell you now is a brief summary, and it will be very brief, just skipping through the different areas in which this is applied. So the core Formal property verification is the main thing that Jasper is known for. To skip on a little bit more to talk about other sort of bug hunting type flows or things that are more sort of procedural. Xpropagation is one that's deployed very extensively by our user base. This is, there's a lot more detail about this that we can go into, but this is basically not gate level Xpropagation checking. This is making sure that your design is X safe. So it employs a non-pessimistic, non-optimistic analysis of the design, injects X's or unknown states into the design at the RTL level, and makes sure that your design is safe against that kind of thing happening. For system-on-a-chip integration, there's a number of applications or automated processes, apps that support that. For example, connectivity verification. So not just point-to-point connections, but also multi-cycle and combinational connections. So that again is a chip level, SoC level. Configuration status register verification. So Steve, I know follow. We have a ongoing date to talk about the register verification. And on the SoC front, that's a fairly rich area of applications for Formal that lie outside the general area in which it's been deployed in the past. So one area that's getting a lot of focus at the moment is an application for low power verification. So using UPF to verify that the low power intent of your design is actually going to still work when the UPF is installed. And there are other areas, the SoC domain that we're investigating. One of this is going back to bug avoidance. One of the key things that we do is focus on the debugging and design comprehension. So for RTL designers, the visualized GUI is a very elegant way of creating properties or assertions about your design and understanding why those assertions fail, debugging back through the traces. One of the great things about Formal is that if you have assertions that fail, you can be very direct to find out why they fail. In simulation, it can be very, very time-consuming to debug. Formal is a great way of doing that. And Jasper's Visualize really makes that we've actually had people say that it is a delight to debug counterexamples using Jasper. I hesitate to suggest that they would then start deliberately inserting bugs simply so they could have fun fixing them afterwards, unless they've got some incentive plan for bug fixing. I don't know. That could be counterproductive. Anyway, and the other one is, well, again, on the bug analysis side, we have some support for what we call post-silicon. It doesn't have to be post-silicon. It could be prototype type. But one of our customers actually debugged. This figure always sounds absurd, but I think it's 190 million gate design using Formal. They had a complex failure in silicon, and they actually loaded the whole thing into a fairly monstrous computer. And other areas that are sort of adjacent to the Formal property synthesis. So looking at a design and synthesizing properties based on either the design structure or the design's behavior, which you can use either in simulation or in Formal. So if we're improving assertion density, for example, then assertion verification flow. There's Formal or the Jasper verification plays a role there. Proof kits, so verification IP, based upon initially a Formal premise. So they're SVA-based proof kits, but they work in simulation just as we do. And the most recent release of those is the ACE coherent. And we are working on others. Another area, which is one for the architects and protocol designers among you, is architectural level applications of Formal. So I don't know if there's anybody that's heard of or used the Murphy tool. Nobody's there we go. Well done, sir. Yes. So we have a tool that works in the same kind of domain as Murphy, but it works off a state table type description and works to provide full proofs at the architectural level. This is a tool that we use with ARM to create the ACE proof kit. So it actually has full coherency checking. So Formal use at all levels in the design cycle, right from architecture through to post-silicon debug. I have approximately 5 minutes left with which to go through what will look like an animated flow. Of all of those apps, what I wanted to do was pick on one, which I think is particularly interesting, and that's the RTL development, so the designer deployment of Formal. And this is one of the areas where I think that the customers that I know in the UK have had the most traction and the earliest return on investment in terms of deployment of Jasper. So often, designers spend as little time as possible verifying before they move on to do the next block. And this is very dependent on company by company. Some designers and some companies insist that designers have bug-free code. Others just say, you write the RTL, toss it over the wall to the verification guys who will fix it. If any verification is done, it will typically be done based on a simple RTL test bench used to bring up the RTL, make sure that it has worked at least once in one scenario, and then after that it's a system verification job. That usually means that really there's little effective verification performed. So this simulation-based flow at an early level really doesn't perform a lot of effective verification. It tends to be focusing on the inputs. What inputs do I need to create to make the output to do what they should do? On the formal side, the visualize technology, which I'll talk about just in a second, actually you take much more of a requirements or an output-oriented view. What should this block do? Create those assertions, and then see if in formal it can make the design do that. And if not, then over that a little bit. So so starting from RTL, the design behavior can be visualized without a test bench. So you're basically creating properties which you then use to get feedback using using this waveform-oriented view about the design itself. So based upon that, and this is now going a step beyond simple formal, but actually now creating a database of expected behaviors from the design, you can start to build up a database of different scenarios which allow you to create different versions of the design, different behaviors that you expect from the design, and build that into almost, it is exactly an executable spec. As you modify the RTL, you can actually check to see what the differences are. So you're doing effectively a behavioral diff between two different versions of the RTL. And any failures, of course, are then clearly highlighted in this waveform environment. So as a tool for early debug and early productivity for designers, it's very, very productive. We actually use this for producing our proof kits as well, because you automatically get from this a live version of the design requirements and the test bench. And those really are the key points. You're doing more verification earlier with less work. And this is one of the things, again, that as I've been learning about Jasper and talking to customers, what has impressed me is the fact that with relatively few properties early in the design phase, you can accomplish an awful lot of verification. One of our customers told me that he was able to keep the design team busy for a fortnight by writing 3 properties about a design. And so from a verification point of view, it was very productive. I'm not sure what the designers felt about that. But no, they were all excited about debugging the property. Everybody's happy. Great. I think we're nearly at the end of the presentation. So from a conclusion, I think the thing I take away from this is it reminds me a little bit of, I can even remember the early days of synthesis, goodness me. It reminds me a little bit of the feeling about RTL synthesis in the early days. Formal verification is able to add an awful lot of productivity to an assertion-based verification flow. Assertion-based verification is a very effective way of instrumenting and debugging and verifying a design. So I think the automation that Formal brings to the ABV flow is going to be a key enabler in promoting that the adoption of assertion-based verification. That's my assertion, I suppose. And as well as a general technology and a general strategy, I think there are very key areas where formal technology, formal techniques are able to bring a lot of value. And would like to know more about any of these in any detail, then do please come and see us downstairs, or just make contact. So I would like to leave you as my final statement with this is the quiz. So again, the key taxonomy for how formal should be adopted is bug avoidance, bug hunting, bug absence, bug analysis, or as Alan Parker would say, aha!
On that bombshell, as Alan Partridge would say. Have you any questions? I do hope you're saving them all up for the panel.
Hi, I'm Ashish Darbari from Imagination. Could you please go back to your last slide? So one of the things that I find quite intriguing and still not quite resolved from the formal technology point of view is, when do you close your verification when you're using formal? If I have a full proof, can I simply close my verification? What is the notion of coverage in formal? What is Jasper's position? Is there a view you have taken? Are there two views?
Okay, so yeah, the question about coverage and formal is a very good one. It's actually the first question that I think Jeff Barrett asked me after I started back in February. Yes, we are looking at coverage. There is a coverage feature as part of Jasper Gold, which will be on mainstream release in the early part of next year. We were one of the companies that demonstrated along with Mentor at DAC integration with the UCDB UCIS database, which allows the cycling of coverage points between simulation and formal. In terms of what formal coverage actually means, I think you've hit upon a very interesting question. I don't think there's a lot of background or consensus about that yet. But again, just one thing I'd like to say as well, I remember the first time that code coverage was released in mainstream simulators. I remember the first time it was released in Model Sim, and we talked about it to all our customers, and they said, well, yes, but what does it mean? I mean, we don't know what it is. It's just, yes, you exercise it, but that doesn't mean you've verified it. And that's absolutely right. And code coverage is a pretty bogus metric for a proxy for simulation quality. But people have become comfortable with how to use it and with experience. And so we're looking at how you apply those same sort of techniques of coverage, cones of influence, constraints versus assertions in the formal space.
Yeah, I guess my question was more on a fundamental level as to what exactly should be the notion of coverage for formal. Mm-hmm. I don't believe the traditional notions of coverage, functional coverage, and code coverage, excuse me, for simulation actually are applicable. And I understand that if you have a simulation-driven coverage metric in place, then you can actually try and merge the results from coverage from formal and so on. But why are we doing formal to solve a certain problem is because we want to get there exhaustively and so on. And then to say that actually I can't get the coverage, so let's harp on simulation, doesn't quite actually make sense to me, if you know what I mean.
No, I know exactly what you mean. I think the issue of what coverage in formal means, in its purest form, if you have a proof for a particular property, all you know is that property as it expressed and all of the logic that is directly implicated in creating that behavior is known to function in such a way that proof is correct. That's only as good as the properties that you've written. Just as simulation is only as good as the way that you're observing the outputs. So, I mean, simulation coverage, as it's used, is a pretty poor proxy. It's just that design or simulation verification practices have evolved around it, that people have developed comfort with it. I think that that's just a process we need to go through with formal as well. We've actually there is a much more technical answer, which I'm not equipped to give you. But we were very happy to arrange for that conversation. thank you. It's a great topic, but one I can't adequately address.
Thanks, Martin. We'll stop them. Okay, so thank you to Martin.